This screencast reinforces some of the main aspects of a TXY diagram for vapor-liquid equilibrium of a binary system. It closely follows Raoult's law. In a TXY diagram, recall that the pressure is fixed. We can generate a TXY diagram by solving for the bubble point and dew point temperatures at various compositions. Even for an ideal system that follows Raoult's law, the TXY curves will not be linear. The pure component boiling points can be obtained at the extremes of the curves, where the mole fraction is equal to 0 and 1. For low temperatures, the mixture will be in the liquid state. For a fixed composition, as the temperature is increased, the mixture will hit the bottom blue curve. This corresponds to the bubble point. The temperature at which the dot hits the curve is the bubble point temperature. The first bubble of vapor will be present in the liquid mixture, with the composition in the vapor phase obtained by drawing a horizontal tie line across to the green curve. As the temperature is further increased, the mixture enters the two-phase region enclosed by the blue and green curves. A horizontal tie line is used to obtain the liquid and vapor compositions. Note that the relative amounts of liquid and vapor change as the temperature is increased. This is represented visually by the bar chart on the right of the screen. When the dot hits the top curve, this corresponds to the dew point. The bar at the right of the screen is completely green, indicating the mixture is all vapor. Further increases in temperature will result in the mixture being a superheated vapor. The dynamic simulation allows us to vary the pressure of the system. We start at a pressure of 1 bar, which is approximately atmospheric pressure. As the pressure is increased, the curves move up, with the boiling points of pure components increasing and dragging the entire banana-shaped curve upwards. A mixture that was initially a superheated vapor can be condensed by increasing the pressure, as demonstrated when the pressure is increased to the maximum level in the simulation. The dynamic simulation allows us to investigate the behavior of the system as we move the cursor around the plot. Horizontal movements correspond to isothermal changes in composition of the mixture. At a fixed temperature, the system can be a liquid, vapor, or two-phase, depending on the conditions. This is an important distinction from the behavior of a single component system, where fixing the temperature and pressure is sufficient to uniquely identify the state of the material. For mixtures, the composition also plays a role in determining the state of the mixture, or whether it is liquid, vapor, or a liquid-vapor mixture. The TXY diagram allows us to rapidly determine the pure component boiling points at the fixed pressure for the plot. Experiment with this simulation to enhance your understanding of TXY diagrams and how pressure and composition impact the separation between liquid and vapor. I would expect you to be masters of navigating these charts and extracting various pieces of information from them.